A thermodynamic system is a region of space or a finite quantity of matter that has a volume and a boundary. The boundary may be fixed or moving. It may be real like a wall or imaginary and arbitrary. Surroundings are anything outside this boundary. System and surroundings together are called the universe. There are 4 types of systems. Number 1. Isolated system. A system which does not exchange any mass or energy, that is work or heat, with the surroundings, is called an isolated system. An example is thermos flask, because water stays hot. That is, no energy goes in or out as heat. Also, water stays inside. That is, no mass goes in or out. Number 2. Adiabatic system. In an adiabatic system, heat and mass are not allowed to be exchanged between system and surroundings. Only work can be given to the system, and also can be extracted from it. An example is any thermally insulated system. Number 3. Closed system. Here, no mass is exchanged between the system and surroundings, but energy as heat or work is allowed to flow in and out. This is also called a non-flow system. An example is a pressure cooker or a kettle. We heat it from outside, so energy can go in and out. But the contents, or mass, remains closed inside the vessel. Another common example you will see in thermodynamics questions is a cylinder and a moving piston. Whatever matter is inside the cylinder is closed off, but heat and work can be given to it. Number 4. Open system. In an open system, both mass and energy can be exchanged between system and surroundings. An example is boiling water, using an open vessel. Heat enters at the base, but also escapes through the top. Similarly, the water also evaporates and goes to the surroundings. So, both energy and heat are being exchanged. So, in the 4 types of systems, the extent to which exchange happens between system and surroundings is in increasing order. In an isolated system, there's no exchange of mass, heat, or work. In an adiabatic system, there's no exchange of mass or heat, but work can be exchanged. In a closed system, there's no exchange of mass, but work and heat can be exchanged. In an open system, mass, heat, and work, all 3 are exchanged. In most thermodynamics questions, we are dealing with adiabatic, closed, and open systems. State is basically the situation or condition of a system. The state of a system is described using its pressure, volume, quantity of matter, which can be mass or number of moles, and temperature. For this reason, these properties PV, Mn, and T are known as state variables. When these properties or state variables change, we say that the system is in a new state. Process is how a system changes from one state to another. There are 4 types of processes in thermodynamics. Number 1. Isothermal process. When the temperature remains constant in a process, it is called an isothermal process. An everyday example is phase change. Imagine water at 0 degrees Celsius is kept in the freezer. After a while, the water will have turned into ice. But the temperature of the ice will still be 0 degrees Celsius. So the temperature remains the same, but the other properties have changed. Another example, commonly used in thermodynamics questions, is fluid inside a piston cylinder which is compressed, and the heat is allowed to escape to the surroundings. Since the heat escapes, the temperature of the substance inside remains the same. So it is an isothermal process. But at the same time, pressure has increased and volume has decreased. Number 2. Isobaric process. The word bar means weight or pressure in Greek and is also a unit of pressure. So isobaric means same pressure, and hence, an isobaric process is a process where pressure remains the same or is constant. An everyday example is boiling water in an open vessel. The water will increase in temperature and can also evaporate to become steam, increasing the volume. But since the vessel is open, the pressure remains constant at atmospheric pressure. Another example, commonly used in thermodynamics questions, is heating a fluid inside a piston cylinder, where the piston freely moves. The temperature increases, and the piston will start moving, so that the fluid can increase in volume. But, since the piston is free to move, the pressure remains constant, as atmospheric pressure. Number 3. Isochoric process. The word choric means space or volume in Greek. So, isochoric means same volume, and hence, an isochoric process is a constant volume process. An everyday example is heating an empty pressure cooker before the whistle blows. The air inside will increase in temperature and pressure until the whistle blows to release it. But before that happens, the volume of the gas inside remains constant, while the pressure and temperature are changing. Another example, commonly used in thermodynamics questions, is heating a fluid inside a piston cylinder, where the piston is restricted from moving, or is fixed. Since the piston is fixed, the volume remains constant. But the temperature and pressure increase because of the heating of fluid. Number 4. Adiabatic process. The word adiabatic means unpassable in Greek. It is used to describe processes where no heat passes between the system and the surroundings. Any kind of insulation can result in an adiabatic process. In industry, we find that turbines try to approach an adiabatic process so that efficiency can be maximized by minimizing heat loss. Another example, commonly used in thermodynamics questions, is a piston cylinder, where the cylinder and piston are insulated. This prevents heat loss. So any processes taking place would be adiabatic. Generally, in thermodynamics, we talk about one more type of process, called a polytropic process. This process follows the law, PV raised to N is equal to constant, where P is the pressure, V is the volume, and N is any number. The earlier 4 types of processes are all actually special cases of a polytropic process, where N is equal to 1, 0, infinity, and gamma, respectively. Hence, polytropic process is a name which can be used to describe almost all processes, but under the condition that they obey the equation, PV raised to N is equal to constant. Equilibrium is a mix of the words equa, meaning equal, and libra, meaning balance. So, together it means equal balance. When a system is equally balanced or stable at every point, it is said to be in equilibrium. When such a system is isolated or separated from the surroundings, then nothing happens to it, because it is already stable. Compared to that, when a system is not in thermal equilibrium, it means it is interacting with the surroundings. So, if we suddenly isolate such a system, then those interactions or processes will stop suddenly. In formal definition, we say that a system is in thermodynamic equilibrium when the properties at all points in the system are the same. These properties may be thermal, mechanical, or chemical. Correspondingly, there are 3 subconditions for thermodynamic equilibrium. Number 1. Thermal equilibrium. The temperature at all points of the system must be the same. So if we took a thermometer and measured each point inside the system, we would get the same reading. Number 2. Mechanical equilibrium. The system must be mechanically balanced. That means there must be no net forces on the system. In most systems we see in thermodynamics, this means that the pressure at all points inside the system should be the same. So if we measure every point using a barometer, we will get the same reading. Number 3. Chemical equilibrium. The chemical composition inside the system must be uniform. It cannot be that one section has only one type of chemical and another section has another type. If we take a sample at any point and test it, we should get the same chemical composition. If all these 3 conditions are satisfied, we say the system is in thermodynamic equilibrium.